Okay, great. So last time, I introduced the notion of the singularity. So if you have any point, and if if you have a function, and if your function fails to be an analytic at some point, then we say the point is a singularity of your function f. And on top of that, there are two types of singularities. Well, the first one is non-isolated singularity. So we are not interested in that type of singularity. So what we're going to discuss for today is the so-called the isolated singularity. So that means if your singularity is isolated, then you must be able to find some neighborhood around the point so that that point is the only singularity on the neighborhood. Okay. Okay. And today, first I want to introduce the singularity at infinity. Sorry. No, not like that. Okay. Okay. Suppose that f is analytic on some analysis okay, so well, this is an analysis, and if my function is analytic on this analysis, then we say f is f has an isolated singularity at infinity. Hold on. So that looks like so why I'm introducing the point of infinity? So I hope you remember this so there was a notion of extended complex plane. So what is the extended complex plane? So complex plane is topologically which is the same as the open disk, right? But if you have just one additional point and you apply so-called the one-point compactification around the point at infinity, then you can actually get a compactified topological space, and which is homeomorphic to two-dimensional sphere, right? So this is what I say, what we call the so-called the extended complex plane. So it goes like this. So we consider a two-dimensional sphere S2 that looks like this. So this is an equator, and this is a North Pole. Yeah, so just any random point, and the another one we say this is a South Pole. But so it looks like these 2 points are very special compared to the other point in S2, but actually that's not true. Well, these are just 2 randomly chosen points from S2. What I want to do is then this S2 minus the North Pole is, if you know just a little bit of topology, then you know what I mean. But if you do not know the topology, but just, you can just simply ignore this. You can simply say this two-dimensional sphere to be a complex plane union with a point called infinity. But if you know a little bit of topology, then I can try to explain like this. This is I have an S2, and if I get rid of the North Pole, then this is going to be homeomorphic to two-dimensional plane, which is also which can be also considered as the C2. Yeah. So this is R2, but this R2 should be considered as complex plane. And same is true if I get rid of the south pole. Oh, well. Then this is homeomorphic to R2, but this is C. So this is what I mean by this entire thing, entire two-dimensional space is the same as complex plane union with some another point outside from this complex plane. So well, yeah, and you can actually merge these 2 points together. Well, actually, I need some kind of operation called one-point compactification, but I'm not that interested. This is obviously out of the scope of this course. So I have these two guys, and these two spaces can be considered to be the same as the complex plane. And each of these complex planes can be endowed with some very interesting coordinate. I say this is this is it, and say that this coordinate, this guy, is endowed with coordinates so-called z, and the same thing is true for S2 minus the south pole. But this time around, let me say this guy is now equipped with the coordinate called W. I'm going to say this is phi, and this is, well, maybe psi, I guess. Yeah. And this is, well, clearly this is a one-to-one and bijective function between these two spaces. And the interesting thing is, our convention is, well, I want to consider composition of these two functions. So what is this? So this guy, well, first I follow this function psi here. Then this entire thing is being mapped to the whole two-dimensional sphere minus the south pole. Now this guy is now being mapped to by the inverse of this function, phi. So this guy, this whole thing is now being mapped to this one, right? Just one exception. Can you realize what it is? Yeah, oh, sorry. Just I need to say just one more thing. Sorry. Such that phi of 0 is being mapped to the north pole and, south pole. And psi of 0 is being mapped to the north pole. So if I take a composition of these two maps, then this is actually a map from C minus the origin to C to C, right? And this function is very interesting. So this function is actually mapping Z to W2, W2 1 over W. So this is C. So maybe you might be wondering, so why I need to impose such a condition? But this kind of composition is very is one of our most favorite convention that is being used in the so-called complex projective space. Well, if you know what it. So this is the usual complex plane that we are working. But so well, so therefore this point is corresponding to the south pole. But here now this guy is being mapped to the everything but the south pole. So this whole thing, well, if you believe in this, then this guy is taking the reciprocal and getting to this one. So the zero in this point should be considered as the infinity in this space. And on the likewise, the infinity at this space should be considered as the zero at this point. Okay, so that means, if my function f, which is defined in this space, is analytic from on this domain, if my function is supposed to be supposedly analytic at this domain, that means from the perspective from this coordinate, then my function is actually is analytic, but not on the origin, but on the deleted neighborhood of the origin, whose radius of the outside circle is precisely, I guess, 1 over R1, right? So f is analytic if my f is analytic at this point, then f of z is f of 1 over w is analytic on okay. And from the viewpoint from this space, I can say, and this point should be considered as an point of infinity on this space. So this is why we are calling this guy, this one, as the isolated singularity at the infinity. Some of you might be wondering, so why we need this point so-called infinity? Because we are living very happily ever after in this space. In this space called the C, equipped with coordinate Z, but well later on. So later on, so we're going to study so-called linear fractional map, and well, in order to get the full and complete picture, then actually it is very natural to assume this extended complex plane. So. So therefore, for the future purpose, I am introducing the notion of the point at infinity. So if your function is analytic entire, then that means your function is on the other side of the sphere. Then the entire function can be considered as a function which fails to be analytic at the origin, right? And vice versa. Okay. Good. And today I want to discuss the 3 types of isolated singularity. If your singularity is isolated, then we can try to classify these singularities, well, just by using the Laurent series of the function around the singularity. Okay, suppose I have a function f, and say this guy has an isolated singularity at point z0. Then, since my singularity is isolated, so that means f is analytic on this deleted neighborhood from with the radius epsilon. And on this deleted neighborhood, we can try to find a Lorentz series of the function f about this point of singularity. Then we have the Lorentz series of f about z0. So okay. So let's say that the Lorentz series of this guy looks like this. From n0 to infinity and an. So this is about the positive powers of z minus z0. And on the other hand, also I have the negative powers of z minus z0. Oh, sorry. Should be b. And to the minus. And suppose that this is true on this analysis. Okay, in this case, the second term, which involves the negative powers of z minus z0, this guy is called the principal part of f at z0. Why this guy is called the principal part of f? Because, this guy is analytic. So for this side, then this summation clearly represents some analytic function. But here, since we are interested in the behavior of our function f, when z is very close to singularity, so this part almost have no effect when z is very close to the z0, right? When z is getting really close to z0, then now this guy will actually be dominating when you try to determine the behavior of your function f. So this is why we are calling this guy to be principal part of f. And just by looking at this side, then we can actually, and it turns out we can classify singularities into 3 different types. So what are these? So I will begin from the easiest case. So case number 1. The Bn equals to 0 for all positive integers. Okay. Then my function, my Lorentz series must look like this. Since I have no principal part here, so, and okay, I should not be forgetting the domain, this annular domain. And in this case, we say Z0 is a removable singularity. Why is it called the so-called? Why this singularity is removable? Well, a prime. Well, technically, my function is not defined on this point, right? Because as you can see from domain, so this function is not defined at z0. But however, I can still fill this singularity by properly defining the function value at this singularity. What do you think is that number? That is, if you plug in just take a look of the first coefficient of this Taylor series. Well, this is, technically this is a Lorentz series, but actually this is a Taylor series, not a Lorentz series, right? So just by defining f of z0 equals to the first coefficient of this Taylor series, then you can actually fill the gap, and you are safe to say my function is actually analytic on this simply closed disk of radius epsilon. Okay, so this is why we are saying this guy is a removable singularity. So since the Taylor series is analytic on the disk. So we can redefine f(z0) to be a0. Then this singularity can be removed. So basically this is no singularity. This is not a singularity. So well, what is an example of this? Maybe I can try to consider this function. 1 minus hyperbolic cosine of z over z squared. Well, clearly, when z equals to the origin, your function is not defined because the z is in the denominator. But maybe we can try to find the Laurent series of this function. And the Laurent series is, well, 1 over z squared times 1 minus, what is the Taylor series of hyperbolic cosine? 1 plus 2 factorial, z squared over 2 factorial plus 4 z to the 4th over 4 factorials, then da da da. So this is just, what is this? Minus 1 over 2 minus z squared over 4 factorials and so on. So this is a, well, even though, well, technically this is a Laurent series, but this is a Taylor series. Therefore, by defining f of 0 equals to minus 1 over 2, then I can say this, well, this singularity can be removed. Therefore, this origin of this function is a removable singularity. Okay. So 0 is an all right. Okay. So the next case is okay. Oh, okay. Yeah. Oh, sorry. My lecture note is kind of messed up. Yeah. Okay. There is the number of non-zero coefficient from your principal part of the Laurent series is only finite. Okay, what does it mean? So, well, this is my principal part of the Laurent series of the singularity, and well, a priori, so you must expect some infinitely many non-zero coefficient of Bn's, but suppose that I only have finitely many non-zero coefficients for this Bn. So therefore, eventually, so every coefficient will turn to 0 if my n is sufficiently large. So in this case, I must be able to find some integer, which I will call m, and m is greater than 1, such that b of m is non-zero, and b m plus 1, and the coefficient whose index is greater than m equals to 0. So this is the maximal index whose such that my coefficient is non-zero. So you must be able to find such an integer, right? Because we are assuming we have only finitely many non-zero coefficients. Okay. Well, so more explicitly, the Laurent series of my function around the singularity is plus b1 over z minus z0 and plus b2 z minus z0 squared and and this expansion ends at bm. So this is actually the principal part is actually the finite sum. Well, of course, on this term. So in this case, we say this singularity is a pole. Z0 is called the pole of order m. And if the order of your pole is 1, then it is called a simple pole. So this is the second case. The second case now. So this is, well, most likely this is the most encountered singularity that we'll be studying in this course. Such as such as z squared 1 minus z. Let me try to find the singularities of this function. Well, clearly, when z equals to 0 and z equals to 1, then my function is not defined, so I can find two obvious singularities. And so how can I determine the order of these two singularities, order of these two poles? Let me try to figure this out. Well, first, when z equals to 0, well, this is a Laurent expansion, Laurent series of my function f around the origin. Then this is 1 over z squared plus 1 over z plus 1 plus and z plus z squared, And obviously, this is true for when z is between 0 and 1. Okay, so can you figure out the order of this pole? Yeah, the order of this pole is 2, right? So in other words, when z is getting really close to the singularity, then my function is behaved just like the function of the rational function of constant divided by z squared. Okay. What about 1? Yeah, so even though, I did not, this is officially not in my lecture notes. So can you figure out, we have actually two singularities. When z equals to 1, yeah, z equals to 1 turned out to be the pole of order 2. What about z equals to 1? So what did I say? Yeah, z equals to 0 turned out to be the pole of order 2. And what about z equals to 1? What do you think is the order of this pole? I guess that should be a simple pole, I guess. Yeah, okay. So if you're not that convinced, real quick, then maybe we can try to find the Laurent series about the singularity at z equals to 1. Or I can say 1 over z squared times I say the -1 z minus 1, and so -1 of z minus 1 goes to here, and this z square, maybe I try to rephrase this guy like this, and plus, yeah, should be plus and minus, and everything raised by 2. Okay, then this is minus z 1 over z minus 1, and inside of this parenthesis, I feel like I have -1 to the n times z minus 1 to the n, from z0 to any 0 to infinity, and everything multiplied by 2. So everything raised by power of 2. So this is what? So this is 1 minus z minus 1 plus z minus 1 squared, and times the same thing. Well, this is just a tedious computation, but well, it turns out that if I multiply, well, you know, you're allowed to multiply these two power series term by term. So this is 1 minus 2 times z minus 1 and 3 times z minus 1 squared, Yeah, I don't know. But it looks like the z equals to 1. The 1 is a pole of order 1, I guess, right? Yeah, must be a simple pole, therefore. Okay. So z equals to 1 is a simple. Okay. So computation of the order of pole is not that horribly complicated. I guess you can easily do that. When your singularity is a pole, then, well, the behavior near the pole is somehow easily predicted by using this theorem. Well, suppose that F has a pole of order m at z0, then as z is getting close to the z0, the modulus of your function around the point should be tending to positive infinity. Okay, so let me prove this. But before we prove the theorem, so I really want you to introduce very important, well, equivalent condition of being a pole of order m. So, well, I want you to recognize this. We should be able to see that F has the pole of order m at z0 is mathematically equivalent to say that f of z can be written as z minus z0 to the m, where is analytic at z0 and is non-zero. These two things are mathematically equivalent. Why? Why is that? this side implication is kind of sort of obvious because well by definition f having the power of order m at z0 implies well you can actually imagine the Lorentz series of your function. Then well and divide everything by well if you factor out 1 over z minus z0 to the m by everything, then well you can actually consider another Taylor series whose leading term is non-zero. Therefore, this is true. Likewise, suppose that this is true, then you can actually also, well, and suppose that this is true, then for the other side implication, suppose that this statement is true, then you can actually imagine the Taylor series of your function f, Taylor series of your function phi at this point. Then if you divide everything by 1 over z minus z0 to the nth, then you can, well, actually, it turns out f has a Taylor series, f has a Lorentz series, and the Lorentz series tells us that the z0 is actually the polar of order n. So they are mathematically. Okay. So phi of z is z minus z0 raised by power of m times f of z. And this is, then this function is analytic at z0. Sorry. Okay, I messed my lecture notice so much today, somehow messed up. So I want to know that the behavior of my function, not my function 1 over f of z, then this guy is, well, since I am talking about the reciprocal of my function f, so z minus z0 goes to the top of the fraction, and phi of z is now bottom of the fraction. And since this is analytic and this is continuous, this is also continuous. So it is, well, this turns out to be, so which equals to 0. So, well, and since, well, 1 over f of z tends to 0 as z is tending to z0. Therefore, well, this is an easy exercise to show that this guy goes to positive infinity. Okay. All right. So, okay. So in other words, I can say if f has a pole of order m at this point, then the behavior, well, even though my function blows up, or in other words, goes to positive infinity, but however, that behavior is kind of tame and very expected. Well, can be expected very easily. But for the last case, I guess this is the hardest case. So, well, this is case number 1, case number 2, and the last case, the last type of singularity is so-called the essential singularity. If there is an infinitely infinitely many non-zero bn's, then we say z0 is called an essential singularity. Okay. What is then example of the essential singularity? I say this function. The exponential function is an entire function, but this entire function has been composed with the 1 over z. So therefore, this function is obviously not defined when z equals to 0. So trying to find the Laurent series of the function, since we know the Taylor series of exponential functions, so all we need to do is just replace every z by 1 over z. So 1 over z times, instead of having z to the nth, but I have the 1 over z to the nth. So this is 1 plus 1 over z and 2 factorial times z squared and so on. Since this is true for this is true for when 1 over z is less than infinity. So yeah. Okay. Some of this is not working. Okay. All right. Okay. And as you can see from this Laurent series, well, I have infinitely many negative powers of z. So this is, well, therefore, this is an essential singularity. And, well, then what is the behavior? Then I really want to say, ask you the same question. So what is the behavior of my function when z is very close to the essential singularity? Now, it turns out the behavior is completely tautological, I say. So we choose any complex number. Say z0. Well, in the polar form, the r0, I say z0 equals to r0 times I times the theta 0. And I want to figure out when my function f attains this very specific function value. So since my function is 1 over z, so I say this is 1 over r times cosine theta, but not plus I times theta, but minus I times sine theta. And I'm interested in finding out the solution of this equation when this guy equals to this. So I have two set of equations. E to the 1 over r, the real part. Sorry, this the real part of here is going to be the r0, and e to the minus 1 over r times sine theta should be e to the I theta 0. So, well, this cosine theta is r times ln of r0, and minus sine theta over r is theta 0 plus, plus some integer multiple of 2 pi. Okay. Okay, so sorry, let me change my expression a little bit. This is sine theta, and this is minus r times, so theta 0 plus 2k pi. Okay, what if I square each of these two equations and add them together? Then r squared times ln r, everything squared, plus r squared theta 0, 2k pi squared is cosine squared sine squared plus equals to 1. So r squared is this guy, and plus this one. Okay. Oh, of course. And the tangent theta is, well, okay. Ln of R0. Okay. So, well, so it turns out if my R, if my complex number Z has this modulus, and if my data has the argument satisfying this relation, then that means I can actually, this function is actually attains this function value, Z0, right? But the thing is interesting because I can actually choose my R to be arbitrarily small. Because, well, because this K integer can be any positive number can be. So therefore, by choosing K to be arbitrarily large, then I can set my R to be arbitrarily small. So what does it mean? So that this means like this. This means for this function, for around when Z is very close to the essential singularity, then for any relative neighborhood of this essential singularity, my function always attains any complex value around that essential singularity. Okay, so in other words, so I can replace like this. Just choose any random complex number you like. Just choose any number. Then then no matter how small your deleted neighborhood around the essential singularity is, but you must be able to find that random complex number as a function value around that, as a function value around the small deleted neighborhood of the essential singularity. Just one exception. Well, you can actually find, well, I was actually lying to you. Well, you cannot get not every complex number around any deleted neighborhood of this point. Actually, there's one number that you can never be able to attain as a function. What do you think it is? 0. This function fails to have, this function can never attain 0 for any complex number Z, right? Because complex number exponential function, it fails to attain, it fails to be 0 for no matter which complex number you have. So, well, this gives us the idea how crazy the behavior of your essential singularity is. Well, when you're getting really close to the behavior of function is getting crazier when you get really close to the essential singularity, because you can actually expect any complex value, maybe except possibly one, but you can actually obtain any complex number as a function value of your function, as a function value of your f. So I can actually summarize this discussion in this one simple theorem, but which is very deep, which is called the Picard theorem. And it goes like this. On every deleted neighborhood, and essential singularity, f can attain any value. Well, possibly one exception. There may or there may not be such an exception, but if there is an exception, then there is at most one point. And finite number of times. So take a small deleted neighborhood around the essential singularity, but you can actually find, well, any complex number can be obtained infinitely many times around that deleted neighborhood. For me, this sounds really pathological and crazy. So let me compare this theorem with this. Well, around the pole of a, well, if your singularity is a pole, then, well, behavior is kind of really very tame and expectable. But on the other hand, if your singularity is an essential singularity, well, it's not the case. So what is the proof of this? Well, unfortunately, the proof of this theorem is beyond the scope of this course. So I may not be able to give you the proof of this. So okay, let me just take this for granted. And since, well, so because of this reason, so I don't want to deal with the essential singularity. Okay. Okay, so this is about the singularity. Now we want to talk about the zeros of the analytic functions. Yeah, I'll begin from the definition. Suppose f is analytic at z0. Well, since, well, if f is analytic, then f is, well, automatically infinitely many times differentiable at this point. If f of z0 equals to 0, and there is a positive integer m such that f of z0 and f prime of z0, f double prime is 0, all the way to the f m minus 1 equals to 0. And if all these numbers equals to 0, and the mth derivative of f evaluated at this point is non-zero, then we say f has a 0 of order m at z0. Well, likewise, a first order 0 is called a simple 0. So in other words, f of z equals to 0 and f prime of z0 equals to non-zero. So, well, so therefore, so as just like we did as in the pole, the singularity of pole, so we can do exactly the same thing for the zeros of any analytic function. So, well, you have an analytic function, and if the analytic function has the function value at z0 equals to 0, then that means that your function f has a 0 at that point, and you can actually define the order of the 0. Okay, and also, just as we did in the poles of singularities, f has a 0 of order m at this point, if and only if f can be written as z minus z0 raised to the power of m times some another analytic function is analytic at z0, and phi of z0 is non-zero. These two statements are mathematically equivalent. So I think I don't need to explain this because, well, you can just imagine, just imagine the Taylor series of f around the point z0, and you can, you can just factor out the factor. You can just factor out z minus z0 raised to the nth power, then you get the idea. Okay, so, well, before we move on, so okay, I want to give you an example of the order of zeros. What about this guy? Z to the third minus 1. Well, I can't expect 3 zeros of this function, right? We'll just, okay, so there is root of unity, so 1 and the 2 other complex numbers. Yeah. And what is in is the order of 1. Order of 1. 1 is clearly 0 of this function, and the order should be 1. Right. So 1 is a simple 0 of this function. Okay? No? No? Well, okay, because, okay, so z0 equals to 1 is a simple 0. I mean, order of 0 of order 1, because f of z, f of 1 equals to 0, and f prime, which is 3 times z squared, and so f prime of z0, I keep writing down z0, is non-zero. So this is a order, 0 of order 1. Okay. Now the next theorem is somehow very striking theorem. If your function is analytic, and suppose that you have a 0 of your analytic function at some point, then you have only 2 possibilities. Your 0 must be isolated. So in other words, you must be able to find a deleted neighborhood around the point, around the 0. And that point, then the 0 is the only 0 around that deleted neighborhood. So this is what I mean by my 0 is isolated. So, there are only 2 possibilities. Your 0 is isolated, or your function is identically 0. These are only 2 possibilities. So, which I will be discussing in this theorem. I have a function. I given a function f and a point. Let us suppose that first f is analytic at z0, and b f of z0 equals to 0, but f of z is not identically 0. In any neighborhood of z0. Then there is some deleted neighborhood around the point, and f of z never be zero for all z in this deleted neighborhood. Okay. So this is zero. So there, that means so in other words, every zero. So if f of z 0 equals to 0, then your function is identically 0, or the 0 must be isolated. Okay, so what is the proof? The proof goes like this. Well, first I consider the Taylor series of f around the point. We consider the Taylor series of f about this point. So it should be look like this. N. Okay. So if all an equals to 0, then f is identically 0. But this is strictly prohibited because of this assumption. So that means at some point you can find some non-zero coefficient in this Taylor series. So I say, so there that means you must be able to find an integer m such that this is the least integer such that the coefficient equals to non-zero, is non-zero. And in this case, well, I can factor out the factor of z minus z0 to the m's, and everything multiplied by some another analytic function, g of z. So this is clearly analytic function. And on top of that, you can actually find out g of z0 must be non-zero, right? Okay. Now what? Oh, right. Okay. So, well, my function g is analytic. Oh, sorry. Okay, g is analytic function. Therefore, g is continuous. Obvious, which is obvious. So, since g is continuous at z0, so therefore, you must be able to find some epsilon such that g of z never be 0 on some neighborhood of around the point z0. Okay, because this is what continuity means. Well, if my function value at z0 is non-zero, then you must be able to find some epsilon neighborhood of this point, so that my function value never equals to 0 in that neighborhood. So this is my argument. Well, existence of such a neighborhood is guaranteed by the continuity of the function g. So therefore, so f of z, which is never be 0 on this deleted neighborhood. Right? Okay, good. Okay, well, this theorem, well, looks interesting, but this theorem actually has very striking phenomenon, so striking result. Well, given a function f and a point z0, let's suppose that f is analytic on some neighborhood. I say n0, which contains this point, and there is a subset of n0 such that S has the accumulation point such that, Z0 is the accumulation point of S. Then f of z equals to 0 for all z in this neighborhood. Do you remember the definition of the accumulation point? What is an accumulation point? So, well, we say this point is, well, suppose that my subset S, has this many points. And if you can find a subsequence consisting of the point in Z, point in S, which is converging to some point, then this point is called to be the accumulation point of this set, right? Do you remember? Yeah. So, or in other words, accumulation point. Well, our definition was actually like this. So, Z is an accumulation point of this. So, if and only if, so every dilative neighborhood of Z0 has a non-empty intersection with, so this is the definition of the accumulation point, right? So therefore, that implies if Z0 is the accumulation point of S, my bad, really, sorry. Forgive me. I missed out one crucial condition from B. Sorry about that. So this is the definition of the accumulation point. And according to this definition, Z0 is the accumulation point of S. And the second condition says that f of z equals to 0 for all z that is contained in the subset S. This implies what? This guy is clearly the 0. Sorry. I must be missing out. So. Oh, sorry. Yeah, sorry. I don't need this. Yeah, sorry. Yeah. Well, and my function is actually continuous on this domain, right? Because, if f of z equals to 0 for every point z in S, that this implies f of z0 also must be 0, right? Right? So that means this is the zero of my function f, but this is not isolated. Okay. And if my function is not isolated, then because of the previous theorem, I must be able to find some neighborhood around of this point, and my function must be identically zero around that neighborhood. Right? Okay. Since f is continuous, so f of z0 must be 0. And since z0 is an accumulation point, of S, so z0 is not an isolated 0, right? Now let me go back to the previous theorem. So, and well, if there is that, it says it has only, we have only two possibilities. First, my 0 must be isolated, and if not, then I must be able to find some neighborhood of z0, and on that neighborhood, my function is identically 0, right? So there is a neighborhood n of z0, which is contained in n0, such that f of z equals to 0 for all z in n. Okay, so this is my neighborhood. So this is n0, and this is the z0, and well, this is my neighborhood of n. And on this neighborhood, it turns out my function is identically 0. Now, what I want to do is just take a positively oriented curve around this, around the point z0. So I will say this is C. Then 1 over 2 pi I times C f of z over z minus z0 to the n plus 1 d0. And you know what? This guy equals to 0. Why? Because C is a curve in this neighborhood. And on this neighborhood, we know this function is identically 0, right? But this is what? This is an. So this is exactly the coefficient that appears in the Taylor series, expansion of f. So that means f of z equals to 0. And since, well, so since the Taylor series around this point is equals to 0, therefore, my function must be exactly 0 in entire of this domain n0. Okay, so this leads us the most important, one of the most important corollaries of the complex analysis, which is called the so-called identity theorem. Suppose that f and g are they are both analytic on some domain D. Let us also assume that there is a subset S such that S has an accumulation point in D and B. Fz equals to G of Z for all Z in S. Then f of z is G of Z for all Z in. So this is versus this. Well, I remember when I was first introduced this theorem. when I was an undergrad student. Yeah, this was very striking to me. So, well, that means being analytic function, being a complex analytic function, is kind of very strong and rigid condition that can be imposed to any function. So that means, well, suppose so consider this hypothetical scenario. So you have a function defined on some closed and bounded vector, so bounded domain, and suppose that you are able to fix the function value on some at most countably many points inside the domain. Then that actually determines your entire function around the domain, right? So this is the identity. Okay, so I think this is for today, and see you next time.